Good morning or good afternoon, everyone. Michele speaking from Enginesoft and the Particle Works team. Thanks for tuning in to this webinar today. We will just wait 1 minute so that people can connect accordingly. There are a lot of registrations, so we'd like everyone to join before proceeding. So just 30 seconds and we can start. Welcome everyone. Particle Works team. And we are based mainly in Italy, and we promote in all around Europe, actually, with our colleagues from Enginesoft and other partners, meshless simulation. So the purpose of today is to introduce you with to meshless Particle Works solver, and so perhaps discussing the agenda and giving you an overview of what I like to discuss, also with your help and your inputs in the second part of the webinar. So first, I will introduce what is meshless CFD, what are the advantages, and where this method can be applied successfully and was applied successfully in new areas of engineering that were previously troublesome for simulation and for fluid simulation or fluid and powder or air coupled simulation. So the main purpose today is really to understand what is Particle Works and what are the multiphysics capabilities in terms of air solver, thermal solver, as well as other feature that we can integrate in our simulation, like particle refinement, non-Newtonian fluids, powders, and fluid structure interaction. And at the end, I would like to have an open discussion with you. We have several industrial case studies in different areas: automotive, food and beverage, pharma, but also cleaning, sterilization, customer care. So I would like you to ask me question, and I can, if possible, show you example of industrial test cases. We have several. So first thing first, why is meshless CFD revolutionizing engineering, and why it's opening up new sector of R&D with simulation? So as you are aware, I think there is an increasingly digital trend in terms of prototyping and product development. This is because on one side, we had several physical constraints in the last years, COVID supply chain constraints, but also price inflation. And at the same time, computing is becoming cheaper and faster. And the complexity also of some products require earlier stage use of simulation. And Particle Works, based on the moving particle simulation method, really allows to open new, let's say, R&D sectors to simulation, because as we will see, the meshless approach, so the fact that we don't need to prepare the CAD, the geometry, but we don't need to simplify it as usually done and so in conventional CFD method. Because of that, we can easily set up a simulation, a CFD simulation that run much faster and gives insight to engineering problems, okay? So this method was proposed in '96 at University of Tokyo by Professor Koshizuka. He is also the co-founder of the developer of the software house. So Promethex Software develops Particle Works in Japan, and we promote it all around Europe. So just to summarize the steps that usually has to be taken in a mesh-based CFD, like several, let's say, solvers are based on this mesh-based CFD, where you have to do very long mesh generation, geometry preparation steps, and then run to the CFD and simulation setup. With Particle Works, we directly work with the CFD setup, and actually thanks to graphic cards acceleration, the solver can be accelerated with GPUs, NVIDIA GPUs. And because of that, we see drastically reduced simulation time also in the hardware part. As you can see here, we have a comparison, and the full simulation workflow, instead of weeks, requires days, and this allows for the investigation of new sectors. So just to summarize here a slide, there is no mesh generation step, so the CAD increases in values because it's not only a designer, or let's say it's not only for production, but can also be used the same CAD for simulation. The simple approach, numerical approach, really opens up the method to a lot of engineers, not only CFD expert, numerical experts. And the fact that we can run on GPUs really lowers the entry barrier in terms of IT infrastructure required for simulation. And here you see the modules that are included in ParticleWorks. So ParticleWorks is not only for fluid model, but also we can have integrated meshless, a finite volume method for air. We have powders modeling as well, we will see, and different thermal solver. So I see there are already some questions. I will just finish this first part, and then I will jump onto those. Thanks for already being so active. So in terms of application and sector, here is a quick overview of where the software is used in the industry. We have automotive application for grease modeling and lubrication of bearings or full transmission, as well as oil-cooled e-motors and piston cooling. We have validation of the method for all of this. And then also mixing of high viscous material, as well as soiling or wading, external aerodynamics coupled with rain, mud, or other environmental, let's say, contaminants, as well as other sectors like hydroturbines. And you can see from the examples that complex geometries, complete geometries can be integrated in simulation without any problem. And also motion can be applied easily. So I will come to the boundary condition capabilities in one slide. But here you see a few examples of where the meshless solver really excels. And that is when we have free surface flow. Okay, so whenever you have flow like jets or like splashing phenomena, particle meshless based method is really advantageous, because here the mesh and the computational nodes are basically where the fluid is, and there is a very efficient way of handling the computational nodes that are the particle themselves. So in terms of, again, the meshless nature of the method allows for easily set up complex rototranslations or combined kinematics. You can also import motion, complex motion laws to the objects. So you can easily achieve this kind of combined kinematics and simulate the full working cycle of the object you are investigating. So here we actually see the air solver, the FVM-based integrated air solver, that is one of the modules that is integrated in ParticleWorks. And thanks to that, I can now discuss the ParticleWorks capabilities. So as mentioned, there is also, together with the particle-based moving particle solver, there are other solver in ParticleWorks. One is the FVM that is coupled in this simulation. You see MPS fluid and FVM air. And the advantages of splitting the two solver is that FVM can then have a dedicated grid size that could be different from the particle size. And there's full coupling and exchange of, let's say, forces and pressure between the fluid particles and the grid. And here is just an air-only FVM simulation. So this FVM solver can be solved, let's say, separately from the fluid, even in steady state. It can be integrated with the MPS, but also with powders. So the powder solver that also is present, and I will discuss in a few slides. Together with the FVM constant grid, we have also a lattice-Boltzmann solver for external, optimized for external aerodynamics. So in this case, you see that we have actually the capability of, of having a refinement of the automatically generated, let's say, Cartesian grid. You see that around the solids, there is a refinement done thanks to the lattice-Boltzmann solver. So it's slightly more advantageous when we are only interested in the air part component and we want to do a transient analysis of complex geometries, moving and maybe like a takeoff of an airplane or whatever. This is all meshless, and the user doesn't have to create a new model. Basically, the same model that can be used for CFD can be used only for air-only CFD or fluid coupled. So we could integrate rain, we could integrate soiling or wading type of simulation to this kind of same digital model. There is also this capability of including a passive scalar to the solver. So basically we can track, let's say, maybe a contaminant or CO2 in this case inside the vehicle, or the dispersion of a chemical that doesn't have different physical properties from the fluid phase, for instance. This is the passive scalar capability is also present. And as far as thermal simulation, also here we have different options and degree of complexity. We could, in the first step, use Nusselt correlation to estimate by convective flow the cooling capability of any fluid. You see here the instantaneous heat transfer due to this water jet on the tool. But then we can increase the complexity. You can see here that the temperature of the fluid can also be analyzed. So basically here we have walls at a given temperature that can heat up the fluid phase, and the fluid can also have temperature dependent viscosity, for instance. So we can have this second type of simulation where we focus on the fluid behavior depending on temperature that evolves based on the boundary condition. And then there is also a conjugated transfer capability. So not only the fluid, but also the solid can be integrated and solved for temperature with a live exchange of boundary condition like heat fluxes between the two phases. Okay, so all in all, this again is with the same graphic user interface, with the same software, with the same module, because the simulation that runs on the CFD can then be with a couple of different settings repurposed for the thermal modeling. So it's very convenient because you have basically one workspace that allows for all of these integrated simulations. One important capability of ParticleWorks when we discuss the fluid part is the possibility to have a multi-resolution region. So basically the idea that closer to the surfaces or in critical areas, we could have an high-resolution region where particles are smaller. So there is a ratio between the two we can define, could be 2, could be 4. And basically the particle size inside here is half, for instance, the particle size outside. And then there is a back conversion, a very stable back conversion between bigger and smaller particles. This is very convenient because maybe there are areas, only small areas of our simulation that requires a small feature of the, let's say, computational nodes, dynamic computational nodes. And that allows, for instance, the study of underhood water intake optimized in terms of simulation times. Basically, you see here a hood with some gaps that in the radiator side. And you can see that basically with 5 millimeter particle size, those gaps were resolved in a better way. But when we go from 10 millimeter to 5 millimeter, the simulation time really explodes from half an hour to 8 hours. Taking advantage of this box, multi-resolution box, inside here we have 5 millimeter, but outside, so for instance, farther away from the vehicle, we have 10 millimeter, and because of that, we can reduce from 8 to 3 hours in this numerically optimized setup. So, by the way, I briefly mentioned it here. The multi-resolution region could be a box, but could also be an imported CAD or volume that defines the multi-resolution region, or also it could be an extruded skin. So you can define an STL or a CAD element, and around that element with a certain offset, we have multi-resolution. We have different viscosity models integrated and capabilities integrated in ParticleWorks, prepackaged non-Newtonian material like grease, chocolate, or mud Bingham model, for instance, but also user-defined rheological curves and tables. And you can basically have shear-dependent or temperature-dependent viscosity without any problem. In terms of like complex materials, we, as mentioned, have also the possibility to include granulates, so solids with a certain granulometry, not only a fixed dimension. And we can couple this GranulWorks DEM, discrete element method solver, with ParticleWorks solvers. In this case, we see MPS coupled with powders. So MPS is the fluid, non-Newtonian fluid in this mixer. And on top, we have the granulates that can be, let's say, like a carbon black to be dispersed, or some sort of powder that has to be dispersed or filler inside the polymeric phase. And in this separator, we have again very complex rotations and the coupling between the fluid in green and the powders in black. This solver lets you integrate rolling resistance, angle of repose, and adhesive forces as well. Talking about the coupling, as mentioned, ParticleWorks FVM can also be coupled to the DEM solver. So here we have a vacuum cleaner type of application where granules are on the surface, and basically you can see here the FVM solver coupled with it at different aspiration rates. This is a fluidized bed where we have some air recirculation system that moves the granulates. And here is also transport with air. There is an air inflow with the FVM solver and the DEM solver for the particle. All of it is meshless, is seemingly integrated without any problem. GranulWorks has also the aeration model. Basically, Here we are looking at air bubble creation and generation and also evolution in several systems like foaming in a gearbox, as well as like air entrapment near a pump in a tank, in a fuel tank, for instance, or coffee cups, or also beer if you want. So basically, the solver algorithm calculates where air will be generated based on the deformation of the free surface, so the entrapment of air and the formation of air because of the splashing phenomena that occur. And then there is a solver, very detailed solver, that can let you understand how the bubble will coalesce and also be transported and then also disappear ultimately. So the lifetime of the bubble can be modeled. Sorry. And lastly, on the capabilities, we have also this model that is for 6 degrees of freedom objects. So basically, inside ParticleWorks, we can define this solid type of boundary condition, meaning that some solid elements, not the tank, but the fins here, for instance, the solid elements that are floating, the screws are modeled with particles, discretized with particles themselves, and they experience gravity. They can move around based on the fluid forces that are generated by the boundary condition that the user controls. So tank and fins are user-controlled boundary conditions, like in terms of rotation and slip. But then the screws or the boat here or the opening here can be influenced by the fluid forces, okay? Interestingly, it's very interesting here to see this case of a sloshing of fuel with this, let's say, baffle that can preferentially open in only one direction. This was achieved with the boundary constraint new feature that were introduced by in the latest version of the software. And here we are also seeing a profile, an acceleration profile applied to the system that causes this sloshing and fluid motion. Okay, so now I can discuss several case studies. We have, yeah, I think more than 30 papers all around different industries. We also have a yearly, let's say, conference that next year will be in Munich in October. And we have proceedings also from this conference from Frankfurt, September 24. In 2024, we hosted in Frankfurt. So again, different type of sectors we could define, we could analyze: lubrication, filling, dispensing, mixing, cleaning capabilities, also e-motor cooling, and so on. So I would like you maybe to first answer the question you had, and then